Hello and welcome to Empowered Learning. This video is going to go over some more examples of calculating definite integrals as well as indefinite integrals. We're going to start off with a definite integral and calculate that, and then for the remaining of these I will be doing indefinite integrals. So I'll be adding the plus c once we do the most general antiderivative for all of these. So for the first problem, you see that we're wanting to find out the area under the curve of the sum of the function that is created by adding x squared to e raised to the x and the exponential 5 raised to the x, subtracting that from those. Okay. So of course here we know that we can take the antiderivative of each of these and then evaluate that from 0 to 2. So the antiderivative of x squared, if we just use our power rule for antiderivatives, and we just add 1 to the exponent and then divide it by that. Of course, the antiderivative of e to the x is just itself. And for the antiderivative of an exponential is just the exponential itself divided by natural log of 5. And we know that because let's say if we took the derivative of 5 raised to the x, then we know that the derivative of that would just be 5 raised to the x times natural log of 5. So in order to get rid of this natural log of 5 here, if we're going backwards, we would have to divide by natural log of 5. Okay, so that's why that kind of comes into being, or why that would make sense, I should say. All right, so let's go ahead and get rid of that and continue on. So now that we have that, all we need to do now is evaluate this, these three terms at 2, subtract, and then do the same thing at 0. So we see that that's done here. And then we do it again for 0. And of course, for our first 3 terms, we'll get 8/3, 2e to the 2, and minus 25 over natural log of 5. And for the second 3, we get 0. We also get -2, and we get a -1 over natural log of 5. Okay. So then from there, we just sort of simplify, and we end up with this exact answer. And of course, you could put that into your calculator and figure out what the exact, what the approximate value is for that. All right, so moving on to example B, this is an example of an indefinite integral. So that means we'll be applying the plus c at the end, recognizing that we know that what we found is actually a family of curves and not necessarily an area, because we're not restricted from one x value to another x value. Okay. So if we look at this, if we take the antiderivative of 3 sine x, we know that 3 is just a constant, so we can pull that out. But the antiderivative of sine is a negative cosine, so we'll put a negative here, and then cosine of x. This 5 is a constant, and we'll leave that out. And if we look at it like that, then we can look at that as 1. And we know that 1 over square root of 1 minus x squared, that is the actual derivative for sine inverse, or arc sine, you may want to call it. So we know that the antiderivative of just 1 divided by square root of 1 minus x squared is just sine inverse. Of course, for the third term, we pull out the constant, and the antiderivative for cosine is sine. And of course, we will append the plus c at the end. So that would be the most general antiderivative for what we have there. So let's move on to the next example. All right, so for this example, we see that we have tangent theta divided by cosine theta. But one of the things that we know is that we can rewrite this way. And if we rewrite it like that, we know that 1 over cosine is secant. And so we have secant theta times tangent theta. If you remember from our derivatives, we know that secant theta is when we take the derivative of that, it will be secant theta tangent theta. Okay, so secant theta tangent theta is the actual derivative for secant theta. So all this will just end up being just secant theta plus c. For our next example, we can rewrite all this in terms of sine and cosine to try to simplify it. And so we know that cosecant is 1 over sine theta times, we know that secant is 1 over cosine theta, and tangent is sine theta over cosine theta. So all of this d theta. Now, if you notice here, we have sine theta and sine theta that will reduce to 1. And we see here we have 1 over cosine theta times 1 over cosine theta, which will end up giving us 1 over cosine squared theta. But we know that the reciprocal of cosine is secant. So really, this ends up being secant squared theta d theta. But of course, we know that secant squared theta is actually the derivative for tangent. So the antiderivative of secant squared is just tangent. And of course, we would obtain the plus c at the end. All right, so for our last example, we see that we're taking the indefinite integral of 4 over 1 minus cosine of 2x dx. And so I note here that we know that sine squared x is equal to 1 minus cosine of 2x, all that divided by 2. So if we take that and rewrite everything, in other words, solve for cosine of 2x here, we see that cosine of 2x can be rewritten as 1 minus 2 sine squared x. So when we do this here, we see that by substituting that and distributing our understood -1 to both terms there, we end up with just 4 dx over 2 sine squared x. And of course, 4 divided by 2, all that reduces to just 2 over 1, which is just 2. And once we do that and we pull the constant out, then we just have a situation where we just have 1 divided by sine squared x, which is the same as cosecant squared x. And of course, if we look at cosecant squared x there, we will see that cosecant squared x, if we make that negative, that would actually be cotangent squared x for its derivative. So what I'm trying to say here is that if we had cotangent x and we wanted to take the derivative of that, the derivative of it is negative cosecant squared x. So if we're trying to go backwards, we know that if we just have cosecant squared, then of course the antiderivative for that would actually be a negative cotangent x. Okay? And so that's why here, after pulling out or factoring out the 2, we have the negative right there, and then we have the cotangent, and then plus c. So that is why I have this note down here, just to make sure that we understand that as far as where the negative goes and where it comes from. And thus we see that taking the indefinite integral of this is relatively easy to do. So this concludes this video on examples of definite and indefinite integrals.